Problem 5, the last problem in section 5.4 is this. The Denver Post reported that, on average, a large shopping center had an incident of shoplifting caught by security 1.1 times every 4 hours, right? It's an average, so 1.1 times every 4 hours. So the shopping center is open from 10 a.m. to 9 p.m., so it's open for 11 hours. Let R be the number of shoplifting incidents caught by security in an 11-hour period during which the center is open. Now, Part A. Explain why the Poisson probability distribution would be a good choice for the random variable R. So Poisson distribution is a good distribution when the probability, when events are very rare and they're independent. So do we have any of those going on here? Frequency of shoplifting is common. No, that's not it. Frequency of shoplifting is rare, okay, and it's reasonable to assume they're dependent. I don't think so. I want independent. Frequency of shoplifting is rare, yeah, and it's reasonable to assume that they are independent. I'm going with that one, but just to be safe, read the last one. Frequency is common. All right, that's not it. So let's go with this one right here. Now, still part A. What is lambda? So what is lambda? Lambda is the expected number. Now look what we're given here. We're given that we catch 1.1 every 4 hours. All right, but now the shopping center is open for 11 hours. So I think what we want to do is find out how many of these 4-hour periods do we have in that 11 hours that it's open, right? So we could write it maybe like this. Out of the 11 hours it's open, how many of those 4-hour periods are there? There's 2.75 of those periods, right? There's the first 4 hours, the second 4 hours, that's 8 hours, and then there's 3/4 left. Okay, now every one of those periods we catch 1.1 shoplifting incidents. So why don't we take that 1.1 and multiply it? Oh, I'll write it like this. You know what? How about 2.75 times 1.1? So that number comes out to 3.025. It is to 3 decimal places. So let's claim over here that lambda, the expected number in 11 hours, is 3.025. Now, part B says, what is the probability that while it's open, the center is open, there will be at least one shopping incident caught by security? Okay, there's that at least one. So I'm going to write that like this. All right, this is part B. Probability of at least one. Now there's, what that means is 1 or 2 or 3 or you see ... You don't know where to stop. So that's why what you want to do is think opposite. And as soon as you see that at least you put 1 minus. Now what is the opposite of at least 1? So look in here. What's the opposite of this? This is the number of incidents caught. 1 or 2 or 3. Well, that would be 0, right? Probability of not catching any of them. So we could do it by formula, right? We could write this 1 minus, okay, it's going to be, right, it goes e to the negative lambda, lambda to the r factorial. So for us it would be 1 minus e to the negative lambda, and that's why they had us get lambda, 3.025 times 3.025 to the number of successes that we want, which is 0, all over the number of successes factorial, 0 factorial. Okay, now this turns out to be kind of nice here because this number to the 0, that's just a 1. This is a 1. So I just have to compute this. Let's do that. So directly on my calculator, I typed in 1, and then I went to get Poisson PDF. Where do you get that? You get it with second VARs. That's where distributions are, remember? And then you have to scroll all the way down to, oh, I forgot which one it was now. C, item C. And then you put in lambda, 3.025. The x value is 0, and you paste, and there comes the 0.95. 0.514. Now, part C is the probability of at least 3. Well, there's that at least 3 again. So, at least 3 would be what? 3 or 4 or 5 or ... You don't know where to stop. So you think opposite. As soon as you think opposite, it's 1 minus. Now, what is the opposite of at least 3? Now, at least 3 means 3 or more. So the opposite would be no incidence, or 1, or 2. Now, I've got a collection here. So I'm going to use my calculator, and I'm going to use Poisson CDF. All right, so let's put in this. So 1 minus Poisson CDF, and I'm using this C because I've got a collection. Now CDF is under second, VARs, that's our distributions. But now you have to scroll down to item D because you want Poisson CDF. Right, and you get that, and it wants lambda. Now we know lambda, that's still our 3.025. It wants the x value, and the x value, that's why I like to write it out, because now I've got the x value right there. It's always the last one that you write in there. Right, so that's my x value. So my x value here is 2. Paste, and then we'll calculate. And when I calculate it, I got 0.58238, but it says to round off to 4. 1, 2, 3, 4, 5, 8, 2, 3, 1, 2. Okay, that's an 8, so I have to round up. 0.5824. So let's claim our answer here is 0.5824. And finally, what is the probability that there will be no shoplifting incidents? That's just going to be this. Okay, we need some room here. This is part D. So in D, we want the probability of none. That's going to be the probability of 0. Now, if I do it by formula, it's going to be, right, the probability of 0 would be e to the negative lambda, lambda to the, looks like an x, lambda to the r over r factorial. So it's going to be e to the negative 3.025 times lambda, 3.025 to the number of successes we want, 0, all over 0 factorial. Okay, we almost did this one not long ago, but we did it with a 1 minus. So this is a 1, this is a 1, so we just need to compute this. And when I did this on my calculator, I got 0.04855, round to 4 places. All right, 1, 2, 3, 4. Now this is a 5, so it's not normal rounding. Remember, we round to an even digit, so I'm going to round that up. Well, it turns out to be fine. 0.0486. All right, so 0.0486. Or if you like, just directly on your calculator. Second, VARs. Scroll down to, now it's just a precisely one value, so we go to C, which is Poisson PDF, and lambda, right, you choose that one, lambda is 3.025, the x value is 0, you paste, and sure enough, I haven't done this, but I should get 0.04855, and then I'll round off and report my answer. And that takes care of all these problems out of section 5.4, and in fact, that's all of them out of chapter 5 now.